I'm gonna talk about part of my research project, which is, so my overall research project is in data-driven, proactive, and predictive maintenance of energy distribution systems. But today I'm only gonna focus on power distribution systems. So first of all, I think it's appropriate to define what predictive maintenance is, and it can be defined as the act and ability to keep something in a good condition by understanding what happens in the future. This stands in contrast to corrective and preventive maintenance methods that are traditionally employed, in which assets are either allowed to run to failure and then corrective actions are taken afterwards, or periodic replacements and preventive maintenance is applied to keep equipment in a good health state so that unexpected breakdowns will not occur. So predictive maintenance is trying to predict when or to what degree problems will happen, so that we have some basis to increase asset reliability and to focus our maintenance actions. In the US, less than 1 in 5 companies employ predictive maintenance in some capacity. And we see here in the right hand figure that the global market potential for predictive maintenance is increasing, and it's increasing at a rate at about 40% annually. So there's a lot of potential for implementation of predictive maintenance applications. In power systems specifically, power outages cost a lot of money. In the US alone, they account for, or they cost the economy $150 billion annually. And a lot of these breakdowns are due to either equipment failure or weather-related failure, which account in combination for about 50% of power outages. And that's an important piece of information because some of the equipment failures can be due to aging of equipment or corrosion, and these things are typically predictable because they change how the equipment behaves, and that can be monitored through continuous monitoring. Also, weather-related failures influence the failure rate of components, and that is also it's usable in building prediction models. So if there's a lot of potential and power system outages cost a lot of money, why isn't predictive maintenance implemented to a larger extent already? Well, some of the problems that we see in power distribution systems is that there's a low sensor coverage. So there's not a lot of sensors on the grid side of power distribution systems. And the sensors that are employed are not high fidelity sensors, meaning that they actually sample with a pretty low sampling rate in some cases. And that's a problem because it limits the information that's contained in the signal. It's not the same for power transmission systems, where there's there's more investments in digitalization, and the payoff is also bigger in transmission system because faults will affect a larger amount of downstream consumers, and so the benefit in transmission systems is higher than in distribution systems. Secondly, at least in Denmark, so my research project, we are in close collaboration with a Danish distribution system operator, and we see that their system is actually quite reliable. So one other concern is that fault data can be scarce or lacking in some sense, and that's of course important if we want to use data-driven, for example, machine learning methods to develop prediction models, because we don't have a large number of training examples for what incipient fault development looks like. So what I try to do in my research is to identify the potential of classes of methods for fault prediction in power systems with limited and low frequency meter data. Notice here I say metadata because I distinguish between data types in power distribution systems. Metadata, with metadata, I mean data collected by sensors, but a large portion of the data that's available from power distribution systems is actually also maintenance records, which are logs of when equipment fails, then what is the underlying cause? And this type of statistical data is also usable to do fault prediction. Secondly, I want to develop methods for fault prediction in power systems with limited and low frequency meter data. And thirdly, I want to field test the developed methods. And that goes in relation to what Bo mentioned in his talks, that it's important that the methods that we develop are actually applicable in practice, so that the industry can also benefit from them. And that's one of the concerns that I've experienced so far in my project, that we actually need to account for the fact or for the state of the industries that we develop methods for. So I propose two different approaches to do fault prediction in power distribution systems. And one is based on using machine learning on this meter data. I considered the use of, as I stated earlier, fault data can be lacking. So I wanted to investigate methods that allowed us to build a prediction model without actual examples of what a fault looks like, because there's a larger amount of data representative of normal operation in power systems. So if we can teach a machine learning model what normal operation looks like, then we can detect when the operation deviates from normal operation and take that as a type of early fault detection, which is in some capacity fault prediction. I proposed some changes to or additions to the standard pre-processing workflow of machine learning, and they are mainly focused on the amount and quality. So the amount of training data and the quality of the training data. First of all, I want to subset data by mode of operation. So these power distribution systems, they are typically meshed grids that have redundant connections. And by switches, you can change the system configuration. So to train one model for multiple system configurations can be a challenging task, because the underlying system behavior is different for different system configurations. That's what I've tried to show here in the left figure, where we see the current at the head of a 10 kV radial, and at some point at around 10 o'clock in the morning, a change in the system configuration happens, and we see that in the behavior of this current signal. Yes, so that's, I want to try to divide this and train models based on each configuration separately. Next, I want to try to investigate whether it's possible to actually combine some of these data sets after they've been normalized as well, because that might provide us with more training data and make model development easier. And the same with the use of VSG, virtual sample generation, which is creating artificial samples based on the distribution of real observations, also in an attempt to add to the amount of training data available. So I've worked with this approach, trying to build a long short-term memory regression model for early fault detection, training it on normal data representative of a normal operation, and then it hasn't been too successful as of yet. We see here in the rightmost figure that the model error leading up to a cable fault And my expectation with this approach was that as the system degrades or the cable degrades, then the behavior of the system will change and my model will fit more poorly as it was only trained on data for normal operation, and then the error would increase as the system degrades. But that was not what I saw, and that can be many reasons for this. But I also considered another approach, which is based on data contained in these maintenance records. I wanted to find or build a prediction model based on the failure rate of electrical components. And as part of this, I wanted to find out what influences the failure rate of electrical components. And I proposed to use correlation analysis for this. And I've started working on this and seen that things like extreme temperatures and loading of electrical components actually affect the failure rates. And it's possible to use this to build a model that can predict the number of failures a piece of equipment or a grid area will experience in some time period. And this is what we can do with this approach. Here I've tried to predict the number of failures a grid area experiences in periods of 13 weeks. We see that it's actually we can actually get a decent accuracy with this type of approach. Now the question is, what are the applications of this approach? Well, some of the things that I consider and want to study further is its applicability to target grid areas for reinforcement or preventive maintenance. So if we know which grid areas will perform poorly, then we can target them for preventive maintenance. But we can also do contingency analysis, so we can investigate, so what are the worst case in system operation and what is the best case in system operation, and use that to plan our maintenance accordingly. Yes, so my presentation was a bit quicker than expected, but that was it. I've included some references and contact information here on the last slide. But if you have any questions, feel free to ask.
I think Daniel.